Hello everybody, in this clip we assign to any lattice in a covariant manner a torus. For this we have first to care about characters of tori. A character of a torus T is a homomorphism chi from T to C star of algebraic groups. The set of all characters of a torus T is a lattice. The addition is defined via pointwise multiplication. If you want to see that this is not just an abelian group, but really a lattice, it suffices to look at the case of a standard torus Tn. Here we have isomorphisms from the n to the character group, sending u to the monomial chi u, which has u as its exponent vector. The other way round, we take a character and send it to its differential evaluated at the unit element. This is just a special case of our general correspondence between integral matrices and homomorphisms of standard tori. Let us see what these characters are good for. Look at the standard torus. The standard torus Gn is the localization of Cn by the product over all the coordinate functions. Consequently, the algebra of functions of Tn is the localization of the polynomial ring by the product over all the coordinate functions. That means we end up with the algebra of Laurent polynomials. Such a Laurent polynomial is a linear combination of Laurent monomials Cu, which are, as we have just seen, precisely the characters of the standard torus Tn. That means that also on a general torus T, every function is a linear combination of characters. It is even possible to recover from the characters directly the group structure of the torus. This runs as follows. The unit element of the torus is determined by the property that all the characters of the torus evaluate on this element to 1. Also, the multiplication map can be determined. It goes from t times t to t, and we detect it via its comorphism. The comorphism goes from O of t to the tensor product of the O of t's, and it sends a character to chi tensor chi. We want to bring together characters and one parameter subgroups. Both fit into a big commutative diagram. What happens in the upper row of this diagram? Look at the pair chi. Lambda chi is a character, lambda is a one parameter subgroup of the standard torus Tn. We take the composition of the two. This is a homomorphism from C star to C star. And we want to know what is the exponent of this homomorphism. This we get just by taking the derivative at the point 1. What happens in the lower row of this diagram? Here a pair uv from Zn times Zn is just sent to the standard scalar product. Now, this diagram is commutative. Here we have the identity map, and here we have our isomorphisms from Zn to the character groups, sending u to chi u, Zn to the lattice of one parameter subgroups, sending v to lambda v. And the commutativity of the diagram is just that we have to compute the derivative of this composition, and this is done like this by applying the chain rule. Now this lower row is a perfect bilinear pairing. That means the lattices Zn and Zn are dual to each other, and consequently the character lattice and the lattice of one parameter subgroups of the standard torus are also dual to each other. This directly generalizes to any torus. What do we have to do? We just mimic the upper row of this diagram, which gives us here a perfect bilinear pairing between the character lattice and the lattice of one parameter subgroups. So also these two lattices are dual to each other. Now we assign to each lattice n a torus Tn. So take our lattice n, take the dual lattice m, and the group algebra associated with m. This is just a free C vector space over these symbols Ku, where U runs through m. And the multiplication is defined by chi u times chi u prime is chi u plus u prime. This looks familiar, and indeed this is a Laurent polynomial algebra. So we know what happens if we pass to the spectrum. The spectrum Tn is a torus. Its unit element is characterized by the property that all these Ku evaluate to 1 on this element. Moreover, the multiplication is defined via its comorphism, sending a Ku to Ku tensor Ku. This construction is even functorial, that f from n to n prime be a lattice homomorphism. Then we have the dual homomorphism of the dual lattices, and this gives us a homomorphism of the group algebras, sending a chi u prime to chi f star of u prime. So we have an algebra homomorphism, and that means we have a morphism between the associated spectra, and this morphism turns out to be a homomorphism of algebraic groups even. Note that we end up with a covariant construction because we compose one contravariant construction with another contravariant construction, namely the second is passing to the spectrum. Here comes a particular example for constructing homomorphisms between the tori associated to lattices. Take a lattice n, then every vector v of n defines as a homomorphism fv from z to n just by sending an integer k to k times v. So this gives us a homomorphism of the associated tori. These are c star in the torus T sub n. So what we get is a one parameter subgroup which we denote by lambda v. And this even sets up an isomorphism between the lattice n and the lattice of one parameter subgroups of the torus Gn, sending v to lambda v. So we constructed our torus associated with the lattice n in such a way that n identifies with the lattice of one parameter subgroups of our n. Here comes the final statement summarizing everything about our construction. It says that we have covariant functors between the world of lattices and the world of tori, both functors being essentially inverse to each other. That means we have a machinery to get from this world to that one, and also machinery to get back, and these two machineries are inverse to each other in a very natural sense. See you in the next clip.